Okay, so we introduced a new vector called electric flux density D. So previously we have the electric field E. Now we got a new vector called electric flux density D. In a dielectric materials, E, electric field, depends on free charge, and it depends on polarization as well, or the polarized charge. The electric flux density depends on free charge only. Historically, D is known as electric displacement field. But in this module, we're going to use electric flux density exclusively. Okay, so we're just going to talk about electric flux density. We're not going to use this term electric displacement field. So every time you see a D, I'm going to refer that as electric flux density. The polarization of the dielectrics P can be found experimentally, and the relationship of that polarization with the electric field can be written as by this equation, which is susceptivity times epsilon naught times the electric field. And these parameters here quantify the strength of the polarization. Okay, it's dimensionless quantity, so it doesn't have a dimension. And it's called the electric susceptibility of the dielectric. Okay, so basically it tells you how well the materials polarize. So different materials has different, I don't know what this called in, what's the Greek symbol of this? Anyone know? Anyway, it doesn't really matter what it's called. Yep. So it's the electric susceptibility of the dielectric. And what it does is quantify how well the dielectric materials polarize. So different materials polarize differently. So which means that different materials will have a different chi or something. I don't know how to pronounce this in Greek. Parameters, and therefore it defines the materials itself. So it's a material parameters. Okay, so different materials, you have a different value for this parameters here. But this is not so popularly used to define the property of the materials. In the next slide, which is the parameters that more often used, which I'm going to talk about in a minute. Okay, so the electric flux density D can be expressed as epsilon naught times the electric field plus the polarization field. And this, we said that just now, is equals to this equation. So if we substitute that epsilon naught E plus this, and therefore you can factor out epsilon naught electric field, you end up with, I call it X plus 1, okay, easier. And this parameters here is known as epsilon R. I'm sure you have come across that parameter. Epsilon R is the relative permittivity. I think you have come across this when you studied the capacitor. I don't know whether you studied capacitor before. So where capacitor if you have a material sandwich between that square capacitor and that materials, different materials will have a different epsilon r. And that depends. If for the same area, if you want to increase the capacity or decrease the capacity, you change that material sandwich between the parallel plate capacitor. Studied that before? No? Okay, never mind. We're going to look at that again in this module. Okay, so that is called relative permittivity. So basically, it also tells you how the materials polarize. Okay, so instead of using this x plus 1, materials normally quantify what the epsilon r is, relative permittivity. Or another alternative terms is called dielectric constant. Okay, so they are the same thing, referring to epsilon r. Whether you use relative permittivity or you use dielectric constants, they are referring to the same thing. So in A, epsilon r is equals to 1. So relative permittivity, basically saying that comparing it to the A, how well this material actually is polarized. So in A is equals to 1. So basically in A is just epsilon naught. Other than A, insulator, then it will be something greater than 1. Okay, so when you have, let's say, PTFE Teflon materials, then you have a different epsilon. So PTFE can be in the value of 2.2 to a range of values depending on the materials. Okay, so this is materials dependent. Okay, so different materials will have a different value of epsilon r, which tells you that different materials will polarize differently. So this leads to our relationship of D equals to epsilon r, epsilon naught E. So in the previous slide, we said that insulating materials, it is easier to work with the electric flux density D. So we find D first, then we work out E from this relationship. Okay, so if you have found what is the electric flux density D, then we can work out the electric field. The electric field simply equals to D divided by epsilon r, epsilon naught. Okay, epsilon r is depend on the materials that you're working on. What's the dielectric materials? Epsilon naught simply just a universal constant. Okay, so if you work out this, you can find the electric field. And that's the reason why we introduced this term electric flux density. So the electric field is the internal, net internal electric field within the dielectric. So remember that we have our materials, we have the applied field, and this is the internal electric field inside the material. What is the actual electric field inside the dielectric materials? Okay, so if you try to find this in the dielectric materials, it's more difficult because we have the applied field, which is free charge, and then we have the depolarization, which is the polarization or polarizing source and sink of the charge. So therefore, we just use or find D, which means that we just find what is the applied field related to, and then we can work out E by applying this relationship. Okay, so This is important equation. You must remember this. Okay, so in this module or any module later on in electromagnetics related, you must remember this relationship. E is equals to epsilon R epsilon naught times E. And this also applied not just to insulator, it's also applied to air as well. So in air, epsilon R is equals to 1, and therefore D simply equals to epsilon naught E. Okay. So in air, epsilon R equals to 1, therefore D is simply equals to epsilon naught E. So you apply to both. So this is to polarizations. This is to free charge in air. Okay, so general note. After this, I'll give you 5 minutes break. So D is introduced at our convenience, and it's not possible to be measured directly with experimental apparatus. Okay, so it's not really real that you can measure. It's just introduced for convenience. And it's solely used as a means to find the electric field. SI units for the electric flux density is coulombs per meter squared, unlike electric field is watts per meter. If the electric field is uniform, the polarizations and the electric flux density are uniform too. If E is non-uniform, then both P and D are non-uniform as well. D is introduced for dielectric, but equally valid for free space. Okay, for free space, simply substitute epsilon R equals to 1. You have D equals to epsilon naught E. Inside conductors cannot be polarized as electrons will move freely to cancel out any polarization. And therefore, P is equals to E is equal to 0 inside conductor. And D is also 0 inside the conductor. Okay, so this D inside only apply inside a dielectric material or free space, and polarization as well. Inside conductor, they are all equal to 0. Okay, I'll give you 5 minutes break, and then we'll come back to finish off the rest of the slides. Okay, we carry on. I don't have a lot more go. Just a few more slides. Okay, so boundary conditions. So we talk about electric field in insulating materials. So just now we talk about if we place insulator in the presence of electric field. Here we talk about boundary. What happens if we have a boundary between two materials or two media Okay, so I have one. There are two conditions or two scenarios. One is the electric field is parallel to the boundary, and the other one where the electric field is perpendicular to the boundary. So meaning that just now we talk about we have a slab of materials. If we apply electric field, okay, so the electric field behave differently. Here, so I have A, and then this is a dielectric. So here the electric field applied is perpendicular to the surface between A and the dielectric material. Okay, here we said that perpendicular component, the electric flux density is the same. So meaning that D1, D2 is the same in this scenario. And here on the top here, if you look at the surface, okay, this area here, the field is parallel. The boundary is parallel. Okay. At the side here, the boundary is perpendicular. On the top here, the boundary is parallel. So for parallel, the electric field is always the same on either side of the boundary. Okay, so it's different. So if the field components enter into a different medium, it's different when the boundary is parallel or when it is perpendicular. Okay, better illustrate using this slide here. Okay, so we have uncharged dielectric interface with free space. Okay, so if I look at these materials here, okay, here is my dielectric materials, and here is free space, air. And now you can see that my electric field component or my electric flux density component, they are parallel to this. So this is my boundary. Okay, so this is the boundary between dielectrics and air. So my field is going upwards, and therefore the field is parallel to the boundary. Okay, in this scenario, we said that the electric field is the same. E is the same. So E1 is equals to E0. They're the same field. And we know that the relationship D is equals to epsilon R, epsilon naught E. Okay. So if I give, so this is A, epsilon R is equals to 1. Dielectric material, we call it E1, so I call this epsilon R equals to epsilon 1, let's say. or simply epsilon r. Okay, in my equation, I just use epsilon r. So the materials have a dielectric or relative permittivity, epsilon r, in the free space is equals to 1. So here, okay, E is equals to D over epsilon r epsilon naught. So we can replace this equation. This will be equals to D1 over epsilon r. So 1 here is epsilon r. So this is epsilon r epsilon naught. And this one, D naught over epsilon naught, because epsilon r is equals to 1. Okay? And they are equal. So it means that D1 over epsilon r epsilon naught is equals to D naught over epsilon naught. Okay, so epsilon naught cancel out. Therefore, D1 is equals to epsilon r D naught. Okay, so the relationship between the electric flux density D1 is equals to epsilon r times D naught if we apply the electric field parallel to the interface. So the field parallel to an uncharged dielectric free space interface, E always the same inside and outside of the dielectric. So the electric field inside E1 and the electric field outside E0, they are equal, they are the same. But D, the electric flux density inside the dielectric, is increased by a factor of epsilon r. Okay, so D1 is equals to epsilon r D0. So I have D0 here, inside here is increased by a factor of epsilon r. Inside here is epsilon r D0. Okay, so that is parallel. The next one is perpendicular. So we apply the field perpendicular to the interface. Then based on rules number 2, okay, here rules number 2, perpendicular, D is the same. Okay, so parallel E is the same, perpendicular D is the same. So D1 will be equals to D0. D1 is equals to epsilon r epsilon naught E1, and this equals to D0 is epsilon naught E0. Epsilon naught cancel out. Therefore, epsilon r E1 is equals to E0, and E1 will be equals to E0 divided by epsilon r. Okay, so perpendicular field, the electric flux density stay the same inside and outside. The electric field inside the dielectrics is reduced by a factor of epsilon r. So the electric field here is equals to E0 over epsilon r. Okay, so the electric field inside the dielectric materials is reduced by epsilon r of the material itself. Okay, so earlier on we said that we have an applied field, EA, and then we have a depolarization field, EP, and therefore the electric field will be EA minus EP. And this is equals to the applied field divided by epsilon r. Okay, we said that the depolarizations trying to reduce the applied field. How much is reduced? It's reduced by a factor of epsilon r. Okay. So is that clear? Parallel boundary, the electric field doesn't change. Perpendicular boundary, the electric field inside the dielectric materials reduced by epsilon r. Okay, this is the last slide. A very common mistake. People always assume that inside the dielectric field, no, the electric field is always reduced by a factor of epsilon r. So normally, people in this area will think about electric field in the dielectric materials. They always think that electric field will reduce by a factor r inside the dielectric materials because of the depolarization electric field. But it's not the case when the electric field is parallel to the interface. Okay, so this is only true if the field is perpendicular to the interface. Okay, only when you're in this scenario. When you apply the field perpendicular to the dielectric materials. If you have the dielectric materials, you apply the field, electric field in this directions, the electric field inside the materials is also equals to EA. Okay, so that is the common misconceptions that always think that the electric field always reduced by a factor of epsilon r. It's only applicable in this case, but not in this case.